Can the light be frozen? It sounds weird, right? And indeed it is. Well, we know that light is the fastest traveling thing in the entire universe. Can you just put it in the freezer and it gets frozen? No, right? Light travels at 300 million meters per second. Now, what is the actual motivation for the physicists and technologists of modern era to hold this electromagnetic radiation in its place? The answer lies to the fact that it paves us to a new era where it retains its quantum coherence properties. By this, it means its information state. And with this, it is possible for researchers to design a new light-based quantum memory. The longer time duration that light can be detained, the better will be for the researchers to the extent that computation is concerned. Hello guys, this is Rupesh Chakraborty. Hope you guys are doing well. You have given me an extraordinary motivation by liking my previous videos and subscribing my channel of Bit Science. Today I have again come up with another new interesting topic. Stay tuned till the end if you want to know it all. Don't forget to subscribe this channel and hit the bell icon to get more videos like this. Now without further ado, let me directly delve into today's topic. We know that light propagates in vacuum with a speed of 3 × 10⁸ meter per second, right? It's a constant. Now, what will happen if it propagates through a material? Then there will be a change in phase velocity of light. We call this physical phenomenon as refraction. Now, how can you quantify rather this reduction of speed of light through a certain material? Here, refractive index of that material comes into play, which is nothing but the ratio between the speed of light in vacuum and the phase velocity. Now, coming to my today's topic, the slow light and the frozen light. This is not what you are thinking, the reduction of phase velocity, rather it is a remarkable reduction in the group velocity. Can we just apply a usually large refractive index and obtain a slow light? No. Let me explain what is happening over here. The nonlinear and quantum optics physicists have established a delicate control over the speed of light while it propagates through a material in recent years. They have manifested that it is completely feasible to control the speed of light from its speed 3 × 10⁸ meter per second in vacuum to only just a few meters per second. IBM has already designed a microchip in the year of 2005 which was capable to slow down light, and it was the first time that remarkably paved the way towards commercial acceptance. Previously, it was in the year of 1998 when a group of researchers from Harvard University and the Rowland Institute of Science successfully designed a slow beam of light, the speed of which was all the way down to about 17 meters per second. It was an absolutely remarkable breakthrough and can be considered as an achievement of milestone of modern age of physics, which was led by Professor Lene Vestergaard Hau. Physicists and technologists continued their research in further slowing down the speed of light. These continuous research efforts have been inspired by the emerging call for designing optical memory, optical buffering, signal processing, data synchronization, which can be incorporate sophisticatedly engineered optically controllable pulse delays. This incessant effort was also deeply motivated for developing computers that will eventually utilize only a mere fraction of the energy that today's machines use. Later came the year 2001 when physicist Hau and her colleagues succeeded in stopping light completely. They developed the methods by which light beam can be completely stopped. These experiments paved the way to another biggest milestone in the transferring of light into matter and then again from matter back into light. This research has a tremendous application in the field of modern quantum encryption and quantum computing. Slow light utilizes the rapid variation of refractive index, which happens mainly in the neighborhood of a material resonance. To obtain slow light in which the group velocity is much lesser than the speed of light in vacuum can be achieved by making the variation of refractive index with respect to frequency large and positive. This is the perfect condition for large normal chromatic dispersion. So what we are having over here is that it is very crucial for us to find a material system in which the said variation is as large and positive as possible. Research has already found an attractive candidate for that, which is none other than a dilute gas of atoms with a strong absorption resonance, which is one of the most promising candidates in which we obtain the variation of refractive index occurs very rapidly in the region of the resonance. Hence, the group index we have here in this system is large. Since the group velocity is the ratio of the speed of light in the vacuum to the group index, as the group index increases, group velocity naturally decreases, right? This describes a possible way to obtain a slow light. Thus, we obtain slow light by the method of propagation of an optical pulse at a very low group velocity. And guess what? Finally, a group of German researchers have frozen this fastest thing of the universe for a record-breaking 1 minute. This paves an extraordinary breakthrough in the field of quantum memory storage and information processing. Now do your maths. Over the course of this 1 minute time span, light can travel over 18 million kilometers, or you may say that it is around 20 round trips to the moon. That's all for today. Hope you enjoyed this video. Don't forget to like and share this video as much as possible with your friends and family. Coming up on the next week with another interesting topic. Till then, bye.